Okay, when we want to calculate the percent yield of a given chemical reaction, we are going to compare the actual yield that is recovered from that reaction to the theoretical yield, that is the maximum amount of product that can be produced from our limiting reactant. And we always define the percent yield as the actual yield divided by the theoretical yield times 100, right, to give us a percent. So to find the percent yield, we're going to follow our basic strategy for all of our stoichiometry problems. We need to start with a balanced chemical equation so that we have our mole-to-mole ratios, and then we're going to use that balanced equation to go from the amounts of each reactant to the maximum amount of product. That is, we're going to calculate determine which is our limiting reactant and calculate the theoretical yield. So to do this, we take each of our reactants and we will calculate the maximum mass of product that will be formed from each reactant. We are then going to compare those values for our different reactants, and the one that is the smallest will be our theoretical yield. Once we've determined that theoretical yield, we will divide the actual by the theoretical and multiply by 100. So here is a common example, or a good textbook example of this type of a problem. So we have a reaction which synthesizes DDT, which is a nasty insecticide which should not be used anymore, but it used to be widespread use in the 70s particularly. And this is a reaction with a compound called chlorobenzene, which has this chemical formula, and a compound called chloral, which has this chemical formula. Okay, and it goes to form DDT with this chemical formula, C14H9Cl5. Let's see if I can, oops, there we go. Okay, so if we have a reaction in which we start with 1142 grams of that chlorobenzene, and we react that with 485 grams of chloral to produce that DDT, and we recover from this synthesis 955 grams of DDT. And we want to calculate what the percent yield is. So our strategy is going to first balance our equation. In this case, we have a balanced equation already. Once we have our balanced equation, we are going to convert the mass of each of our reactants, 1142 grams of chlorobenzene and 485 grams of chloral. We're going to take each reactant and calculate the maximum amount of the product that we can form from that amount of reactants. And we're going to repeat this calculation for both of our reactants. So we'll start with our chlorobenzene. So we have 1142 grams. I'm just going to call this CB for short. And we're going to convert this to moles of chlorobenzene. So we need to calculate the mass of 1 mole, or the molar mass. So we're going to take the usual strategy, 6 carbons, 5 hydrogens, and 1 chlorine, and that will give us a molar mass of 112.5 grams. So we've converted grams of our starting material to moles of our starting material. Now we're going to convert that to moles of DDT, and finally to grams of DDT. Okay, so we will convert 1 mole of DDT, which is this guy. 1 mole of that is produced from the reaction of 2 moles of our chlorobenzene. Okay, and finally we are going to convert from moles of DDT to grams of DDT. So again, we need the molar mass. Now for this one, 14 carbons, 9 hydrogens, and 5 chlorines gives us a mass of 354.5 grams of DDT per 1 mole of DDT. Again, our units are canceling as we go along here, and we're left with mass of my product. Now, we could have stopped at this stage at moles of my product and later converted this, but it's really not so much more work to do this one more step in our calculation. So we're going to go in our calculator. We get 1142 divided by 112.5 divided by 2 and multiplied by 354.5 tells us that if we react all of our chlorobenzene, we'll get 1,799 grams of DDT. Okay. We're going to repeat this calculation for our mass of chloral. So we take 485 grams, I'm just going to call that C, times 1 mole of C per, in this case, the molar mass for chloral, 2 carbons, 1 hydrogen, and oxygen, and 3 chlorines gives us 147.4 grams of C per mole. So my units cancel. And I'm going to again use my mole-mole ratios. We get 1 mole of DDT for every 1 mole of chloral that we react. And our last step is the same, 354.5 grams per mole of DDT. Okay, and then we punch our numbers into our calculator. 485 divided by 147.4 times 354.5, telling us if we react all of this, we will get 1,166 grams of DDT. So now comparing these two values, we have almost 1,800 here and less than 1,200 here, telling us that the chloral is our limiting reactant, and this is my theoretical yield. Okay. If I use up all of my chloral, I can get a maximum of 1166 grams. Okay, so in order to react all of my chlorobenzene, I would need to be reacting much more of this chloral. So this is my theoretical yield. Now in my problem, it tells me that I'm producing 955 grams of DDT. This, different color there. This is my actual yield. Sorry about that. So this is my actual yield right here, 955 grams. So to get the percent yield, I take that actual yield, 955 grams, divided by my theoretical, which I just determined was 1166 grams, and I multiply that by 100. So I take 955 divided by 1166 times 100 gives me 81.9% yield. Okay, and so this number tells me the efficiency of my chemical reaction, or the efficiency of my recovery in this particular process.